In this lab of the GEOL 2017 course, Geology for Engineers, we are going to discuss about igneous rocks, but mostly we will focus on rocks that are really shallow, so they form in shallow conditions, so subaerial conditions, as well as rocks that tend to form, igneous rocks that tend to form in hypabyssal settings. So these rocks, if you remember from the lectures, are related to the processes of volcanism. In this figure you can see clearly examples of emissions of materials of a volcano, and these are the different explosive activities that commonly are found in stratovolcanoes. This example is likely from the South American volcanoes, but we have seen that pretty much all the subduction related magmatism can have a component of explosivity, which is essentially linked with the processes such as partial melting, in which we have a lot of contribution from the crust that will enhance the amount of silica of the magmas. So the explosivity is typical of these settings, but also it will be found in intracontinental settings for the same reason. So if we have hotspots that are localized inside a continent, we will have still relatively explosive magmatism taking place. So with this, we have essentially a bimodal behavior. So we develop commonly pyroclastic products, which are those clouds you see in the figure. So a lot of fine-grained material is expelled from the volcano in the form of fragments and also cinerites when they are extremely small in size. But also we have lavas that form, and you have here an image of a stratovolcano with the alternating deposition of tufts, which are the light gray material, which is fine-grained, but usually is essentially the result of precipitation of pyroclastics or the result of ignimbrites, so pyroclastic flows that accumulate on the side of the flanks of the volcano. The second important process is the formation of lavas. These are not ejecta, so that's the key difference. These products will be deposited on the flank of the volcano, but they form a flow that is emitted from the main crater, and usually it is very similar to the movement of a river, especially in volcanoes that are characterized by extremely fluid lavas. So in this context, then the lava can be partly ejected, so you can still have ejection of lava fragments, which will form characteristic ejecta such as bombs or cinders. But mostly the lava will be essentially flowing from the rim of the crater directly on the flank of the volcanoes. So today we are going to look at these aspects. We are firstly going to review some of the stuff we discussed earlier in the previous lab, so some of the terminology and I have included in the lab paper a quiz that sort of will help you sort of memorizing some of the terminology, because this part of the identification of rocks is really relying on a number of terms that are descriptive terms which are used to help with the description of the specimens. During the oral examination, two factors are critical for your success. One is that you describe really well what you see in the pictures that I will provide, as well as describing also and determining more correctly the name of the rock specimen that we are examining together. So these two factors, description and classification really of igneous and volcanic rocks and plutonic rocks will be critical. So I will give you some examples in this lab of the type of pictures that will be provided to you, and also some examples on how you should describe the different specimens. And yes, today the focus will be on the volcanic rocks, because in the previous lab we already discussed the plutonic rocks quite extensively. You can practice by sort of looking through the web at some pictures of rocks and sort of try to at least to describe 10, and also focus on a variety really of rock types. Consider previous rocks. Okay, so I've cut this and I'm going to redo this slide from this point. Good, so in this lab we have an introductory part that deals with the terminology. So you have to complete a quiz, which will come in the next few slides. We will discuss that more in detail, but yes, this is a quiz mostly based on terminology. We are going to review some of the terminology, and this is because for your oral examination it's important that you do two things. The first one is to describe what you see. So if you get a specimen, I will send you a picture or share a picture on Dropbox, and you just have to describe well that specimen, as well as the second most important point is really to define a name for that specimen. So these two things. So this is why terminology is important. You will have to use it and learn it when you describe the rock and discuss it with me. Today's lab is really focused on volcanic rocks, because so the effusive variety, because we discussed the plutonic in the previous one, but let's really focus on these descriptions. Make sure you complete a number of descriptions, at least 10. I would recommend at least doing 10 that sort of consider really from the standpoint of describing the rock. So practicing in describing rocks is important for then your oral examination. Consider also ultramafic rocks. We are going to look at some of the ultramafic rocks that are commonly found on the planet. So kimberlites, komadites. These are usually rocks that form really deep and are part of a particular style of magmatism, so hotspot related magmatism. So they will be a little bit distinct from the classifications that we use to represent the most abundant igneous rocks, I would say. In fact, if you take, a rhyolite or an andesite, so effusive rocks, usually these are more abundant than kimberlites and also komatites as well, because they are more restricted examples, really, because they are essentially associated to processes that are more rare. Okay, so if we look at the terminology, we have a number of terms. So we start with porphyric or porphyritic. This term is used commonly to describe hypabyssal rocks, in which you have that phenocrysts are well developed, but they are usually contained in a matrix that is microcrystalline. So it's represented by the same mineralogy, but at a smaller scale. Phaneritic, if you remember, phaneritic rocks are rocks like granites or diorites or gabbro. So rocks that have a mineralogy that you can recognize easily with a naked eye. So that means that crystals are well developed usually. The contrary is true for aphanitic varieties. So an obsidian or a basalt could be aphanitic because you don't see really well the crystals. So you need a hand lens many times to be able to understand the mineralogy of the rock. Amygdules are really the infill or the cement that infills a vesicular basalt. So all the vesicles get filled. So this cavity is filled with different mineralogy. If you remember, we discussed the amygdals as having different composition. We'll see some examples, I think, of those today and discuss this aspect. But yeah, essentially they are cavities that form because of the degassing in usually a vesicular basalt. So vesicular is then a term that is quite often added as a prefix to a basalt to indicate that it does have a significant amount of vesicles, which are quite visible, and this is a good indication that you had a lot of gas separating off the magma. An holocrystalline rock is a rock that could be considered a phaneritic rock, but yeah, most of the rock is represented by crystals essentially. So that's the idea. In some cases, you might have holocrystalline rocks that are not really phaneritic because the crystals are too small. Another rocks are those that have essentially mineralogy that is anhedral. So when a crystal doesn't really display a proper geometry or symmetry or habit, in that case the mineralogy is anhedral. So the rock could be considered as composed by anhedral minerals. If you remember, we have all those other terms, so subhedral for an intermediate situation, euhedral when you have really crystals that are well developed and they have a proper symmetry. And then we finish with pyroclasts, so these ejecta fragments essentially of a variety of rocks. We'll see today different types of tuffs which can be, composed of pyroclasts that are either vitric, lithic, or crystals. So remember, vitric stands for glassy, lithic stands for rock fragments, and crystals, of course. These are essentially minerals, well-developed minerals that are included in this pyroclastic material. So, complete the quiz. It's included in your lab assignment. So the second one, and this is really a summary of the quiz. So just a question of filling in with these parts with the minerals that are mafic and felsic, and then look at terminology to describe volcanic and plutonic rocks, and then we have several terms that describe exactly what I was mentioning. So the appearance, so you will have to fill it in with rocks that actually match. So for example, a pegmatitic granite in this case would be fine. Then give a definition of the phenocryst. So what is a phenocryst? And then here you can discuss examples really of euhedral minerals and which are commonly found in a variety of rocks. So this could be an euhedral pyroxene, let's say, or a subhedral quartz, and so on. And then we have melanocratic, mesocratic. So if you remember, this refers to the color of the rock, so you should use a rock terminology that actually matches. So a melanocratic rock could be, for example, a gabbro. So we could call it a melanocratic gabbro if it's really dark. Pyroclasts, we will see these sizes later, but yeah, I would list here for reference the size of the different pyroclasts. And this is just for yourself to remember the distinction between vitric, lithic, and crystal, which I already mentioned. So for the main groups of minerals, remember that we have this basic classification of mafic, so the dark colored minerals, which are olivine, pyroxenes, amphiboles, and the biotite. And then you have the felsic, which are the light colored minerals, so those are the quartz, the alkali feldspar, the plagioclase feldspars, and muscovite mica. Common accessory minerals will include the iron, titanium oxides, so the spinel. We have discussed that in the virtual experience, and also the sulfides. We mentioned those, and we saw also the apatite with that characteristic hexagonal section. And then we have some that we didn't really review because they're quite rare, which are the zircon and the sphene. Just keep them in mind for future reference, although they will be not part of this examination. Here is the Bowen sequence. We looked also the Bowen sequence. It's important to revise this because it's the most useful diagram to identify the associations of different minerals. For example, at the beginning, when the rock is at a high temperature and it's solidifying, it tends to have that the magma is relatively mafic, and so we have calcium-rich plagioclase together with olivine and pyroxene that will constitute your ultramafic peridotites. Then we go into mafic gabbros. So the gabbros and basalts quite often have a combination of pyroxene, amphibole, and plagioclase. And then we move down and we have these intermediate rocks, which are diorite, andesites, and these will have combination of minerals. So in this case, with this slide, we are reviewing the Bowen sequence that we discussed extensively during the virtual experience when we were looking at reconstructing the Bowen sequence with the minerals, but in this case we are associating those groups of minerals with specific rock types. So in this case the diorites, the andesites, so those will have your biotite, some amphibole, some pyroxene, and more sodium-rich plagioclase present. And then we have these felsic assemblages, so granites, which were already discussed, and then rhyolites, which are the effusive equivalent. So remember, for basalt, andesite, and rhyolite, those are effusive rocks. They have the same, respectively, the same composition of a gabbro, or of a diorite, or a granite. So granite will contain quite often, we have seen that, quite a bit of quartz, so between 20 and 60% quartz. And then we have potassium feldspar, so K feldspar, muscovite. These are the classical really minerals you find. So muscovite and biotite could be present in a granite, and the same is true for rhyolites, although rhyolites are glassy, so they tend to be different in a way. So the distinction will be on the phases, but the composition will be similar. So this is another diagram that shows the same concept, but it adds another dimension, which is the concept of proportion of mineralogy. So the volume of minerals as a percentage is represented on the y-axis. So you can get the feeling, for example, of how the volume of amphibole increases progressively, going from rocks that are relatively poor relatively rich in silica, and down this side with rocks that are relatively poor in silica, which are the ultramafic rocks. So there is a kick in amphibole that is a good indication that you are in an intermediate rock, which is quite important and will be helpful for the classification of some of the intermediate rocks, for example. Then we have, the existence of muscovite and biotite. If you can detect in a rock muscovite and biotite, you have quite a bit of silica because of the association to quartz. So you can see the volume of quartz, how it drops progressively, and it's actually leading the way to an increase in volume of plagioclase feldspar. So there is essentially an anti-relationship between the alkali feldspar and quartz, which tend to decrease progressively towards intermediate and basic rocks, and the plagioclase feldspar, which tends to increase in those intermediate and basic and ultra-basic assemblages. Okay, so these are good indications. So if you find a lot of alkali feldspar, lots of muscovite, and some biotite, well, that's a good indication you are in a rock that is relatively silicic. If you have that you are replacing progressively the biotite with pyroxene, then you enter in a field that is more typical of gabbros or tonalites. Those rocks will be relatively low in pyroxene, relatively low in biotite, and have a much more pronounced increase in pyroxene content. And the same is true for olivine. For those ultramafic or ultrabasic assemblages, they tend to have much more olivine in them, as you see from this diagram. So the volume progressively goes up until you reach the peridotite that have more than 90% of olivine, and in those circumstances you enter the field of the dunites. So it's important to look at a comparison between volcanic and plutonic rocks In this case, we are looking at a plutonic rock, which is again a rock that forms at significant depth, so usually more than 2 kilometers down, and therefore it does have time for crystallization, and because of that you will obtain these textures that are, a rock that is holocrystalline, so crystals are well developed, and also it's a phaneritic rock because you can see the mineral assemblage without use of a hand lens. In this particular specimen, we can see a set of colors really for the minerals. Some are really white, which are likely plagio-clays, and then you have quite a bit of K-feldspar, which is this pink to yellowish color, and then you have dark gray plugs or LUTs that are representative of quartz. So an example is here of interstitial quartz, and also we have darker minerals, we like this example here, or this lamella here, which is a good indication that we are dealing with a biotite. So biotite is present. Remember that during the examination you can ask me a question about the hardness of some of the minerals that you are identifying in the rock. So you could ask me the hardness of the dark mineral, like this plug in here, and I would tell you that it's around 2.5, and so that's a good indication that you're dealing with a phyllosilicate. So it's a good way to distinguish, from amphibole or pyroxene, a phyllosilicate, because those silicates tend to be higher in terms of mass scale, so they will be around 6, so 5 to 6, and that's a discriminating factor. So if you use the pin nail, for example, you'll be able to scratch the biotite on this rock specimen, but you will not be able to scratch an amphibole, and there might be some amphiboles sometimes in these intrusive rocks. The equivalent of an intrusive rock of that type is a rhyolite. So this is the effusive equivalent. So if I form a lava of an intrusion that was crystallizing granite, it will be likely a rhyolite. That is quite often exemplified by the color. So sometimes the pinkish color is allusive to the presence of K-feldspar. So alkaline lavas containing a lot of K-feldspar are usually classified as rhyolites, and quite often you will recognize also the presence of biotite. So dark flakes of biotite are also a good indication that you are dealing with a rock that has a significant amount of phyllosilicates as well as tectosilicates like feldspar. There are also fragments of glass in this specimen, which are characteristic with this gray color and vitric luster, and those will be relatively hard. So if you ask me the hardness, I would say that this fragment has a hardness of 7, and so it is easily understood that a rock that is relatively high in silica will have free quartz, and this free quartz is a good indication that this is likely a rhyolite. Okay, so remember, the rhyolite is an extrusive equivalent of granite. It can contain glass fragments as well, so these fragments are not necessarily quartz. Most likely they will be amorph silica, and they the rock usually has an aphanitic texture, so you are not going to see very much the mineralogy if you look at a specimen with a naked eye. You need really a hand lens to be able to recognize some of the mineralogy because the grains will be very small. So it's usually less common and less voluminous than granite, and that's if we think about bathylitic provinces, for example, the Andes, certainly the distribution of these lavas are usually restricted to the volcanic cones. Instead, a bathylitic province, it's much more distributed widely, and because of that, it's a good sort of indication of the different proportions of these products. So remember, you usually have to fractionate an intrusion, but the resulting magma or the melt is a small component of the entire. So the melt that separates usually it's a lower volume if compared to a larger intrusion that crystallizes at depth. Another important comparison that we need to make is the mafic one. So if we look at the gabbro, so we are, on a range of silica that is much lower. So gabbros are down here. So we have, between 53-54%, and in some cases less than 50% for gabbros of silica. But so dominantly the gabbro will be composed of two minerals. It's usually common to find gabbros that contain 50% plagioclase and 50% pyroxene, although they can contain also small amounts of amphibole as well. But these rocks usually have very little quartz, and it's not commonly visible in the rock. So the equivalent of a gabbro, it's usually a rock that is called basalt. So the basalt has the same composition, but quite often and you will not be able to see really well the mineralogy. So you need to enlarge or magnify the specimen with a hand lens, and then you will be in a position in which you can see some of the plagioclase as well as some of the pyroxene that is present. Sometimes these basalts can be olivinic, so they can contain quite a bit of olivine, especially if we are going towards picritic compositions, so compositions that have more magnesium rich melts, and so tend to ultramafic essentially compositions. One good example are really high temperature varieties of magmas that we will see later, which are the komatites. So in Archean terrains, komatites quite often contain really abundant olivine. But we have other examples like the Hawaiian volcanoes that tend to erupt fragments or crystals of peridot, which are related again to the fact that hot spots usually source the magma at sometimes more than 400 kilometers of depth, and because of that they have contamination from mantle that is significant, and so they have ultramafic compositions that lead to the formation of extensive amount of olivine. Okay, so these are the most common, really extrusive rocks. So the rhyolites and basalts should be rocks that you are easily recognizing using this specimen. Is quite gray, but in most cases the basalt will be really dark and look commonly black in color, and this is related to the abundance of pyroxene really in this rock. So if we recap, if you remember, we have mentioned the Strachyzen classification and the same type of ternary diagrams. So here we have two ternary diagrams, one that is used for the classification of foids or foidites, which are rocks that are usually they contain relatively low amounts of silica, and on this other you have the silicic rocks. So you tend to have ranges that go from rocks that have less than 5% silica up to 90%, in which you have quartz-lites, so rocks that are extremely rich in quartz. But yeah, most of the rocks that we are going to look at really are in this field, exception made for the foidites here. So remember, we have the rhyolites and the basalts, but we have also other terms that are used to describe a change in content with respect to this A and P. So this is commonly called an AQPF diagram, and that's because you have alkali feldspar in here, quartz up here, and this is the plagioclase, and those are the foids, which are the leucitites. So leucite and nepheline quite often are silicates that form when you don't have enough quartz or silica in the magma to crystallize feldspar. So they replace essentially the plagioclase and also the K feldspar or alkali feldspars. So if we discuss the compositions here, you can see these rhyolites can be extremely rich in alkalis sometimes. So alkali feldspar can be really abundant, so you will call it an alkali feldspar rhyolite, which is usually a rock that has more than 90% of the feldspar will be represented by the alkali feldspar. But yeah, quite commonly all these rocks fall into the field of rhyolites, and then you have dacites, which are rocks that are instead represented dominantly by plagioclase, so the sodic and calcic varieties. And then if you drop the amount of quartz and you enter in fields in which you have rocks still dominated by alkali feldspar but have less quartz, you start to consider them as trachytes. And if you have a mixture of K feldspar and plagioclase, these will become latites. And then when you have the rock becomes when the rock becomes okay, when the rocks becomes particularly dark, and then we are in a basalt or an andesite, which we commonly distinguish because of the abundance of amphibole. Usually andesites can contain quite a bit of amphibole, as we will see later. Okay, these are the silicic ones. If you go down here, we have usually tephritic rocks versus phonolithic rocks, but they are a bit out of the scope of this course. Remember, when you see a lot of rounded white phenocrysts in a lava, most likely they will be foids, and this is sufficient really for the classification of foidites. We will not venture too much in the distinction of tephrites versus phonolites because it's quite challenging. Pyroclastic rocks, yes, the classification usually it's based on the phenocrysts that you can recognize and also the fragments because these are really assemblages that form by deposition of a variety of fragments which have also different size, and in fact also the classification is based on size as well. So quite often a sinerite, so a rock that has fragments that are very fine grained, will be termed a tuff, and so the ash is usually less than 2 millimeters, so ejection of ash that is less than 2 millimeters will produce essentially the deposition of layers of sinerite that consolidate and become a tuff. So the tuff can have a variable composition because of the explosions that can break part of the volcanic cone, and since that is composed of rock, it will form rock fragments during explosions, and this will contribute to the lithic component of a tuff. So if you can recognize a lot of irregular fragments, you can say that the tuff is a lithic tuff. If you instead can see a lot of crystals, so feldspar for example, or plagioclase, or maybe biotite in a rhyolite tuff, in that case you would call it a crystal tuff. And instead, if you have a lot of glass in the rock, you call it a vitric tuff. So if we move away from the tuffs that can have variable compositions and increase the size of the fragments up to 64 millimeters, we call them usually lapilli, or a lapilli tuff if it's a compromise between tuffs and lapilli stones. And if we go down this way, we will increase the size of fragments that contain of, let's say, a pyroclastic deposit that contains blocks and bombs that are usually composed of fragments that exceed the 64 millimeters. So in this case, you start to talk about the lapilli tuff breccias and then pyroclastic breccias or agglomerates, especially if they have been resedimented. So pyroclastic rocks, remember, are rocks composed of fragments that are ejected during the volcanic eruptions, and to provide a summary, these have different varieties depending on the size and composition. So we have the tuffs, which will be ash-sized fragments, and the volcanic breccias, which are particles that are usually larger than the ash, so the lapilli and the bombs. If we give some examples, you can see clearly very light in color, so white tuff in this case, and this is a lithic tuff because you can recognize the edges of rock fragments contained in the tuff. A tuff is quite easy to recognize because of the low density. Usually it's quite light in terms of weight, and it can be quite spongy as well. In some cases, white fragments like these are termed pumice, especially if they can float on water. We will see an example in the lab, so when we do the third virtual experience and we review some of these rocks, you will see that they can float quite easily on water. Other things you have to describe really well the fragments in this case. So describe the color of the fragments, and you should test them with the acid. Of course, I can do that, and we can infer the composition of the fragments, which could be, 30 fragments of sedimentary rocks or volcanic rocks. So existing silicic glass can be fragmental and will be part of these lithic assemblages. So different compositions are possible. Carbonatic will be possible as well. In some cases, you might have pre-existing sedimentary rocks that are involved in the pyroclastic processes, and these will be trapped as fragments. In this example, for example, I can see this dark gray fragment, but also more whitish fragments, and also more yellow-brown fragments. So these, could have different compositions. Some could be pre-existing pumice, other could be more mafic composition, so more basaltic fragments, depending on the different eruptive phases that have characterized the volcano. So we can see that the manifestation of eruption can be diverse depending on the period of eruption so that the volcano is experiencing, and the relationship with other factors such as the interaction of water. So we saw that when we have calderas or Mars, we can form lars and other types of resedimented material, volcanic material, and these will be all part of this explosive activity. For example, if we look at another tooth, we can sometimes have tufts that have quite a bit of glass in them, and if the deposit is very rapid, and so you get a big thick layer of tooth, you tend to compact the tooth, and if the tooth maintains, because of the insulation that is arising from the thickness of the sinerite, if it maintains a relatively high temperature, we have a tendency of compacting also and reshaping glass shards, so glass fragments. So these black crystals are, or amorphous crystals, are actually fragments of glass. You can differentiate them from crystals of biotite because they are very dark, so they could be confused with biotite based on the hardness, so they will be much harder than biotite. And also, if you look carefully, they form lenses, so they tend to have a morphology that gets thinner while we move away from the center of a glass shard, and that's the result of differential compaction taking place on these fragments. So they were really hot, and so they could flow, and so you have differential flow of glass and recrystallization that tends to form this lensoidal morphology. You have down here a description as a good example. I'm not going through this description, but it does say pretty much what I've mentioned. Some other more clear examples of the shards. Of course, the glassy appearance. So in this case, a vitreous luster is also a diagnostic feature for this particular specimen. In some other cases, you might have additional fragments that you can localize, so we could infer that these are fragments of K-felspar, so they could be either lithic fragments or crystals that have an alkalic composition, which would correspond to a rhyolitic eruption, which is justified also by the abundance of volcanic glass. If you instead have crystals that are so abundant, you will call this, rather than a vitric tooth or a welded tooth, more likely a crystal tooth like this. And so if it's andesitic in composition, it could be also lava. So depending on really the weight of the specimen, you can quite often differentiate between a rock and a tooth. Also, usually when the composition is really homogeneous, like in this example, this is almost a porphyry. So I could define this more correctly as an andesite because of that. So in this case, I would call this rock an hornblende andesite, and I would carefully examine the crystals and try to understand if we are dealing with pyroxene or amphibole. So remember to look at the basals and also at the cleavage of the crystals. In this examination, you will ask me questions about the different phenocrysts, and we can discuss them together and sort of reach a conclusion with respect to the main mineralogy. So if these mafic phenocrysts are dominated by hornblende, like this example here, we tend to classify the rock as an andesite because of that, because it's more an intermediate composition. A good indication that this is hornblende is also the color of this rock. It tends to be extremely greenish, and often hornblende will have this characteristic green color. So remember, hornblende is a type of amphibole. And the composition of the hornblende is usually sodium or calcium rich. So remember, it's a ferromagnesium silicate. So one of those ribbon-like silicates, and has also quite a bit of calcium in it. Here is another example of andesite, but in this case we identify this rock because of the abundance of plagioclase. So we have quite a bit of phenocrysts containing dominantly calcium-rich feldspars and sodium-rich feldspars. So the albites will be critical, and as well as the anorthosite varieties. So this is a good example of andesite because of the proportion of felsics versus mafics. So quite often a porphyry of this type, which could be also defined as a diabase. So you can call this also an andesite porphyry, just because of the type of texture that you can observe. So it's really crowded. We have many phenocrysts of plagioclase with different orientations. And yes, there is also the fact that this rock is in a matrix that is really dark. So we have a microcrystalline matrix which will be dominated by plagioclase, but also really abundant pyroxene as well. So the rock contains, on the order of 30% plagioclase, and usually has really little biotite, so there will be hardly any phyllosilicates in here, which is a good indication that you are dealing with an andesite. Usually andesites have quite a bit of quartz in them, but it's not going to be visible, and so the amount of silica will be relatively low, and so the andesite will fall under the 5% quartz really. Okay, one last thing for this specimen. Although we're calling it an andesite here, it's really difficult to tell apart if it's a rock that is a basalt or an andesite because of the dark color of the matrix. So in this particular case, only by looking at thin sections we will be really in a position in which we can differentiate between these two varieties. But yeah, we have cases in which it's much easier, so especially if you have large volume of amphibole, you will be able to make that distinction. Here is another example of basalt, but this is a pyroclastic product. So remember that 64 millimeters subdivision when we classify the ejecta based on grain size. So in this case we have a particular type of bomb which is essentially shaped like an almond, and it's quite commonly characterized by a crust that develops because of the rapid cooling during ejection. So a bomb usually is a large fragment of magma that is ejected at a relatively high altitude. It can travel for significant distances away from the main crater, and during this time it will essentially modify its shape according to the aerodynamics of the motion. So we tend to have basically that it gets very smooth on the surface, and also it's basically forming essentially a pointy tail, which is the result of the air interacting with the melt and remolding essentially the shape of the fragment with the attrition of the air against the surface of the fragment. So rapid cooling will produce this crust, which are quite characteristic. This is a breadcrust bomb. Many times the bombs will form cracks, especially when after the impact, when they are deposited on the flank of the volcano. The impact and the cooling that occurs very rapidly will cause a fracturing of the crust, and this gives the characteristic appearance similar to bread. So this is why they are called breadcrust bombs. In section you might see also a variable amount of vesicles, so we could call this a vesicular basalt, but that's for the composition of the bomb rather than the morphology. So remember, the rock will look pitch black and usually has a smooth rounded surface, and it's quite often rich in vesicles. In this particular specimen we have more than 70% of the specimen is characterized by vesicles. In some other examples, the vesicles will be forming amygdals, and this will be infilled by a variety of cements. These can be quartz or alternatively carbonates. Of course, during the examination, we'll be able to test some of these hypotheses by looking at the reactivity of the rock. So if I tell you that the white amygdals react to hydrochloric acid, that's a good indication that those will be carbonatic in composition, so they will be essentially dominated by calcite. Other cases will be rather greenish, and those are commonly represented by epidote varieties of amygdals. So the epidote usually appears in green, pistachio green colors, and does not react to the HCl. In some other cases, the presence of clays will be dominant, and you have also things like this very nice fibrous amygdal, which is whitish, more dull in color, and it's represented by zeolites that are actually associated with clays, and they form the infill of this particular vesicular basalt. So sometimes zeolites, which are phyllosilicates, really that are part of the family of clays, will tend to represent some of the amygdal composition. This is another example of a relatively dark rock, but you have to be very careful when you look at these rocks. So volcanic rocks are more challenging to identify if compared to the plutonic rocks. Here it's critical to recognize the pinkish color of the phenocryst, which is a good indication that you are dealing with quite a bit of K-felspar in this rock. The fact also that there is no clear evidence of volcanic glass is telling us that we are likely dealing with a lava that is mostly devoid of abundant quartz, and so we would be definitely under the 20% or even less than that, so even less than 5. And this is why we could call this rock a trachyte. So the fact that we don't see really a lot of quartz, and so no glass fragments or quartz fragments, and also we have still some biotite present, so we can recognize some of the phyllosilicates that are an indication of the association with K-felspar, but we lack the quartz, so we cannot call this a rhyolite, and we have other mineralogy, so the phyllosilicates are quite abundant and give this darker color to the microcrystalline matrix, which is a good indication you are dealing with a trachyte. Another example here of a tooth. In this case, it's a lithic tooth. So we've discussed lithic tooths, and you will get those that are relatively light in color, so white, but also darker variety, like these examples. And of course, that's a function of the type of rocks that are involved in the explosivity processes. So whenever there is an explosion, depending on the composition of the cone, you will get a particular type of tooth. In this case, this is classified as a lithic tooth, again because of the abundance of lithic fragments, which are usually of variable size, so in equigranular, and also very irregular in their morphology. Here is an example instead of a characteristic texture you will find in comadites. So remember, comadites are ultramafic mantle-derived volcanic rocks, so lavas that tend to crystallize of relatively picritic compositions of magmas, so magmas that are really olivinic in composition, so they contain a lot of magnesium. These were also really hot, so they could flow really like the Hawaiian volcanoes, lavas, and so they could form essentially rivers or flows of lava that would lead to the formation of things like lava tubes. And because of that, within a particular section of lava, you can identify often spinifex texture, which is essentially a texture that arises from the slow cooling of just below a crust of magma that formed on the top of a lava flow. So many times these spinifex textures will be regular and radiate essentially vertically with respect to the direction of flow. And the crystal can have a variable size. They can exceed sometimes the metric scale, so more than a meter, or they can be relatively small, so on the centimeter scale, especially when they are crowded like in this example. So here this lava has been altered, so quite often the olivine is replaced by chlorite, but you can still recognize the original shape of the crystals of olivine, which in this case are bladed and essentially form these elongated luts. Another example here of the same rock variety, in which you can see better, because it's less altered, the distribution of these olivine crystals that have been partly substituted by chlorite, and that's because they look completely different, much darker in color. So that's a characteristic texture that is certainly a good way of assessing the type of lava you're dealing with, and it's a good indication that this was an ultramafic rock, so in particular comadites. So the comadites will have this unique, really, pattern represented by olivine crystals. Another unique rock is the kimberlite. We have discussed kimberlite pipes and presented some examples. So this rock, you could confuse it with a lithic tooth, but in reality it's very difficult to do so because of the density. This rock will be much more competent, more dense, and so heavier, and is usually represented by fragments that are more rounded. You can see clearly that the edge of the fragments is quite often very well rounded. And this is an indication of the high level of explosivity that occurs in kimberlite pipes. Another diagnostic feature is the fact that you can recognize crystals of olivine or in some cases diopside will be a little bit darker in color in terms of the green. So the evidence of magnesium-rich silicates is also a good indication that you are dealing with a kimberlite. Often you will find magnesium-rich olivine and fragments that are sort of constituted by chromium pyrope, so you will find also garnet in these rocks, which is quite distinctive. Other things that could be in a kimberlite are carbonates. So sometimes you will find carbonate veins. So there are some examples of this vein on this particular specimen, and so it will be reactive to acid. And so definitely a good way to differentiate between, for example, an andesite and a kimberlite would be really to look at this type of enrichments in carbonate. Here you have an example of the existence here of xenolite, which is essentially a fragment that has been included in the ultramafic magma and has partly also reacted with the magma itself during crystallization. So these are good indications that the fragment was present in the magma and sort of reacted with the surrounding melt. This concludes the lab. So we have sort of reviewed some of the rock types that are more critical for this examination. So in this lab, remember it counts for roughly 30%. It will be examined on 3 minerals, 3 plutonic rocks, and 3 volcanic rocks. A series of photos will be shared on the day of the examination. We will have essentially an examination that is a one-on-one test in which I will ask you a series of questions about the things that I have discussed in these lab lectures, as well as during the virtual experiences, so the other videos. In terms of marking, again, I really emphasize the importance of describing well your specimens. So if you describe well things like grain size, texture, and you also recognize some of the mineralogy, that will be enough really to get a good mark. If you are considering also the nomenclature and do that properly, it will be even better. But yes, the name of the rock is not so critical, and that's because sometimes it's very hard macroscopically to attribute a proper name. So it is acceptable to make some misclassifications, but at the same time, if you are able to classify the rock properly and describe it well, you will get the maximum points. Finally, here is an example of a description. You had many other examples, so remember to focus on things like color, size, and also some of the terminology that I have illustrated at the beginning of this lab. But then also talk about the mineralogy, since we spent some time looking at a variety of minerals. It's important that you are familiar with the basic ones that are present in both the plutonic and volcanic assemblages. And then naming the rock is really the third aspect. So this completes this discussion. I leave you with the virtual experience on the plutonic and effusive rocks, and also please complete the lab paper number 2, which will give you sort of an overview of the things that are important for the description, classification of these specimens. In the next lab, we change subject. We will be discussing more sedimentary rocks.